in which we'll be discussing about decision trees. We'll start with very simple and then we'll build upon from there. So let's start with a very basic understanding of what is a decision tree. So if I have a decision node of anything, so suppose if I have a classification problem in which I have some data, I have some features in that data, I have a class of the or labels for this data, okay, whatever we are trying to achieve. So suppose I have two features, x1 and x2. Let's assume it is the blood pressure that we are measuring, systolic blood pressure and diastolic blood pressure. So these are some features. Okay, and my labels, or you can say it y, might be if such a person has gone to a doctor or has taken something like a treadmill test, what has been the condition of his heart. So heart condition is my y variable which I'm trying to predict. So suppose someone has got a systolic pressure which is 80 and 150. I'll not use these numbers because this is continuous data. We'll deal with these later. So we'll convert them into classes. So suppose between 80 to say 90, we are calling it low. So this is low, this was 90, this is also low for me. And above that, suppose it is 95, I'll call it high. Okay, and similarly, there are a few more instances of high, which can go up to say 100. So this one is 100. My diastolic blood pressure may have like a lot of range, so I can have three levels into it: low, medium, and high. So suppose 150 is medium. Okay, then I have 120, which is low or okay. 130, let's call it again low. 140, or let's just be very high. 150 is actually high if it's in a normal state. 140 is say medium. Again 130 we can call it low, and 145, this is medium. Okay, I will not be using this continuous number, so I have crossed them. Now suppose we have no labels for these. So for this high and low, suppose my risk condition was low, okay, or a low risk sort of a thing. So this one is low risk. Okay, this one is low risk. I'll just use the word L. Low, again low risk. Let's call this as high risk. Okay, let's see it later. So this one is high risk. Okay, this one is high risk. Okay, and this one is a low risk. Now, if I take my blood pressure now, I will obviously not have these because these have come from either a doctor or the treadmill test or similar test. But I can obviously measure my blood pressures over there. So if I want to make a system that can help me understand what is my risk level, such that I can go and just measure if it's coming into the high risk, I can go and consult my doctor. Okay, so I want a system to do that. As a human, I can say very colloquially, if you have like a high systolic and a high diastolic, you should actually refer to a doctor. Okay, then get it tested. But what if I have like a high systolic and a low diastolic? Okay, low systolic and a medium diastolic or a high diastolic. In this, I'll say it will depend. A lot of things can actually come into picture, but we do not have enough data. And that is how humans work. We make rules out of these discrete variables. This is exactly how decision trees will also work. Whereas models like neural networks or other linear models can actually do a lot of, you can say, more complicated design of these things. But we want something simple that we can actually refer to in RST. This is what decision trees is. So to understand decision trees better, we'll have to first understand how do they work. So decision trees have three things. So the first thing is you choose a purity measure. Okay. Second thing is algorithm for growing the tree. This should encompass your split of the nodes. How do you split the nodes? Okay, and this will also encompass what type of variables you can deal, x variables that you can deal with, and also the type of work that you can do. Can you do only classification? Can you also do regression? So y type. And the third would be how do you avoid overfitting into such a tree? Overfitting treatment. So next, let's understand about the purity measures. So what is purity? Okay, purity can have different measures, but it says after this particular split how pure the data is from before the particular split. So let's understand something to start with, which is information. Okay. So in probability, any event delivers a particular information, but the probability of an occurrence of an event is inversely proportional to its information that it delivers. So for example, if my heart pressure is always 120, which is the normal, I again measure YT 120, it doesn't give me enough or good information. It's the same old information that I have. Now there's very low probability that I get a heart rate, suppose which is 100, 150. But if I happen to actually get something like this is a critical condition, has a lot of information built into it, and I should actually take action. Okay, unique action. So the probability of this is very low, whereas the probability of these is very high, but the information delivered by this is very high, whereas this is like a normal information or low information. So after we have defined or at least got some measure of the information, let's understand what is entropy. In chemistry or in physics, entropy is the state of your randomness. Okay, or in chemistry it is more of the heat, or in physics it is random. But in one form of another, it is about how haphazard things are, or how noisy things are, or how much energy, or the, you can say random motions are there in those things. The same happens with data also. So in the case of data, if the data has a lot of energy into it, which is in the form of you can say information, then it has a high entropy. So if there are too many classes interacting with each other in the same data set, we'll call it very high entropy data. So entropy could be defined as your proportion of the data, okay, and multiplied by the information that it contains, or you can call it log of information. And information was inversely proportional to 1 by p. So you can say something like this. Now 1 by p is equals to p to the power minus 1, and anything that is minus 1, so log of anything, say x raised to the power minus 1 could be written as minus 1 raised to the power log x. Okay, and if I'm taking a natural log or log base 2, we can say ln. So we will say this is p2 minus 1, so minus times p log of p or ln p. Okay, so this is the information of a particular data. Now in the initial data that we had, let's see what is the entropy of this. So if I'm taking my y variables, there are 3 conditions which were low risk in the whole data and 2 conditions which are high risk. Okay, so out of 5 data points, I have 3 which are low risk and 2 which are high risk. So the entropy of the system is 3 by 5, of course will be minus sign, log of 3 by 5. Okay, this minus sign is from the log part, 2 by 5 which is a proportion, and log of 2 by 5. Okay, so let's call this as the entropy of my initial data. So now I'll use the symbol D for complete data set. And now I'll be using these symbols instead of the actual numbers, whatever they are coming. Now the first decision that we have to take is whether we should be dividing the data in the first instance by systolic pressures or diastolic pressures. Okay, so let's assume if we want to do it by systolic pressure, what is the information gain or entropy of the resulting split. So now there are 2 which are low risk on systolic and 3 which are high risk on systolic. So if we divide by that, these 2 will go on one side of the node and these 3 will go on the other side of the node. And if we see for these 2 that is going on one side of the node, 2 are low and 1 is high, and for the right hand side both are high. So if we are dividing this by systolic, if I'm using a systolic pressure to divide it on the low side of the systolic pressure, my split of the data is 2 is of one class and 1 is of another class, which is 2 is low risk and 1 is high risk, whereas on this part I have 1 is low risk and 2 are high risk. I think it was 2 and 0 for low systolic and 1 and 2 for high systolic. Okay. So this is 2 and 0 and this is 1 and 2. 1 is low risk and 2 is high risk. Okay, so let's compute the entropy for the split of the node. And if you see, we have 5 data points total, out of which 2 have gone over here and 3 have gone over here. Okay, so later on we'll take the weighted average for the splitted nodes such that we can compute the total entropy of the data, again a weighted entropy. That is why these numbers are required now. But first we'll compute the entropy of each every part of the split, and then we'll compute the entropy of the data after the split. So in this particular case, what is the total? 2 data points minus log of 1, 2 upon 2. Okay, log 1 is 0 and then this is again minus 0 into whatever log. So this would be minus 0 and minus 0, which is equals to 0. So the entropy of this side of the node is 0. We have pure, no randomness in this. Everything is very stable, very consistent. So entropy is equals to 0 for the split of S low. Let's compute the entropy for this part. So we have 1 by 3 of log of 1 by 3, okay, and 2 by 3 of log of 2 by 3. Okay, so let's call it as entropy of my systolic split where systolic is equals to high. Okay, so what is the entropy of the data after the partition? We can say entropy of the split, systolic split, is equals to the weighted average of the individual splits, which is 2 by 5. So 2 data going over here out of the total 5 into this particular node, into the entropy of this node, which is 0, okay, plus 3 by 5 and entropy of this split of the node, so into E S SH. So if we do a split on systolic node, this is the entropy of the data after the split. So what is the information gain that we have? Which was entropy of the data before the split, which is entropy of the complete data in this particular case because we had no split earlier, minus entropy of the data after the systolic split, or information gained by systolic split. Okay. Similarly, we can compute information gain if instead of splitting it by systolic, we split it by diastolic pressures. So split diastolic, which will be equivalent to entropy of the data minus entropy of the split from diastolic. And how we will actually do a diastolic split? Again, the same way, we'll take the whole data set over here, so 5 data points. Then we'll take the diastolic node, and then now diastolic had 3 levels, high, medium and low. So we'll do a 3-way split. So this will be our diastolic low, diastolic medium and diastolic high. We'll see how many data points are coming in each of these split, and we'll see the y variables, how many, what is the count of the y variables low or high. So hard condition low and hard condition low risk and high risk, and do the count over here, and the same formula will apply, and then we'll do a weighted average across the weights, which is the number of, or the proportion of data points which are going over there. That will give us EST. Okay, so whichever has a higher information gain, we will decide to split by that data. So suppose systolic has a better information gain, so we split the tree. So this is my whole data, and after that I'll say systolic is high or low. So this branch will become systolic low, and this branch will become systolic high. Now I have only one decision point after this, which is the diastolic. So each of them can have a diastolic branch. So this is diastolic low, diastolic medium, and diastolic high. In the case of systolic high, if you had seen, in the case of systolic low, there was no other branch. So this is already a pure branch. So it will not require to split further by diastolic. So this part is not required. So the tree ends over here because this is a pure node. Entropy is 0. So you cannot actually split it further. Whereas these would be splitted by your diastolic low, medium or high. It may be that in one of this there is no data at all, so that will go. So let's see if we had any data for systolic high, which is low. Systolic highs have medium, low. There is no high. Okay, so we can actually get rid of this. So this part will not be there. Okay, so this will become a decision tree. This is how do you do it. The type of decision tree that we discuss specifically is called ID3. Well, very popular and simple decision tree. Okay, then you have something called C4.5 and evaluation of that called C5.0. what both of these could do is they both can deal with continuous variables also. So for example, now I suppose do not have my the levels of blood pressures as low, medium, high, but exact blood pressures. Okay, so for example, now I have my systolics in the range of say 80, 85, 90, 95, so on to say 100 or 110. Okay. Now the risk profile that we see for systolics again without having any other information on what is happening. So up till here, say 80 to 90, we are low, suppose, and then we started going till 95, we are low on Y, and then we started going high. As of now, we do not know the position of the other thing. So let's call it low, 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 low. And suppose in one of these, it is very high, so it started coming again high, but it went low again, and then high, 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 high. So okay. So now obviously logically there is no point of splitting the data anywhere here. So this doesn't make us split, okay, because everything is continuously low even before this and after this. What are the possible split points? So one is this split point is possible because after that you have got a high, and we do not know whether this is just a noise point or this is the right split, or a right split could come over here which is this is a noise point, or this is high because of some other factors, not because of systolic. Okay, and then the third split could come over here, and after that it's again high, so there is no point of splitting over here. Now the algorithm C4.5 or C5 will actually try to make these three splits and try to see the entropy of these splits if they were splitting it by systolic. So they will call this entire portion in one go, say as systolic to level 1 or class 0, systolic class 0, and this they will treat as systolic class 1. In the second iteration, they will apply up to here as a systolic class 0, this split point, and from this split point onwards, they will call it class 1. In the third split, they will start obviously with this split point. This whole would be C0, and the last part, this part, would be C1. And then whichever gives a better entropy gain, they will use that as the splitting point. The other variable can be continuous, like this they will do a treatment of the other variable, otherwise it could be categorical, in which case the treatment that we described would happen. There's another problem with the purity measure that we took, entropy or information gain. If you saw or noticed earlier, suppose in this particular case, so this was 0 and this was like rewarded very highly, which is good. In this particular case it was a coincidence, but many a times if suppose you choose some measure which has a lot of splits into it, or there's a lot of levels into that attribute, that lot of levels will lead into a lot of split, which means that many of the split will be pure. The data either would be there will be no data, or data would be completely of one class, and information gain tends to sort of give a fillip to those sort of conditions or attribute variables. So they will keep that as the most important attribute. Despite the fact in real life condition it may not be so. So to avoid those sort of a thing, you can use something called a Gini index. That is what I suppose C5 does. Instead of information gain, you can use a proportion of the information gain. So one way is this. So you take the information gain divided by your number of splits. Okay. One way is this. Okay. The second way is that you can use Gini index. This is also a good way to use it. These are the two ways that you can deal with purity, but these are not in ID3, other trees. Okay. Then what happens if my Y, which is a health condition or heart rate, is not like low, medium, high? So in this case, my heart rate was low, medium, high, or low or high. Okay, but suppose instead of just consulting a doctor, I am made to do a treadmill test, and the treadmill test actually tries to see at a particular inclination how many seconds do I survive on the treadmill. Survive I means I get exhausted and leave the treadmill. If that is my y variable instead of this low and high, then this is a continuous y variable. So this is suppose 30 seconds, this is say this is coming lower, so 25 seconds. Okay, 20 seconds, it's only 10 seconds, 10 seconds, 8 seconds. Now this is my variable. This is a continuous one. So I cannot deal with the continuous y variables in the case of the earlier trees that we discussed. So something like a card tree can come over there. So these are different types of trees. Next we'll talk about the ensembles of tree. We have left the topic of overfitting. We'll cover that in one of the next videos. So in the next videos we'll do ensembles, and then we'll actually have one more video for the overfitting of the trees. Thank you.